prize session. My name is Klaus Bartschat. I work at Drake University and I have the privilege to chair this session, and I was also privileged to chair the committee that selected Professor Michael Allan for this prize. And in order to introduce him, I thought I would just read one sentence from all the letters of support that were given for him. And so let me just do this. So sorry, I have to get a piece of paper. I don't know them by heart. So first one says, Professor Allan is one of the most distinguished experimental scientists of his generation, with much of his outstanding work being of direct relevance to the gaseous electronics community. Another letter said, Michael's experimental apparatus, particularly his trochoidal monochromator, is unique and superior to any other similar equipment in the entire world. Another one said, he is well known for having pioneered low energy differential scattering electron spectroscopy to as low as 0.1 eV incident electron energy, which is incredible. I'm a theorist, but I believe that is true. The next one said, Michael's work was highly independent. On almost 50 papers, he took responsibility as sole author. At the same time, he strongly supported his students and was open for cooperations with other experimental and theoretical groups in cases where he could provide essential data to make progress in the understanding of the topic. And the last one says, I'm also impressed by the degree to which Michael has collaborated with theorists. This reflects not only his high regard in the high regard in which his measurements are held, but also the extent to which his results have interested and challenged theorists. Well, I can certainly testify to that because we had some very nice collaborations, and it was always a pleasure to work with Michael. So as a one more technical thing, please, in case you have a question, just put it in to the Q&A box. I will watch that box. And I will then, at the end, read the questions to the speaker. So don't wait until the very end. There could be a delay, and so it's important for us to know these questions early. Thanks a lot. Welcome, Michael. Congratulations again for winning this prize. Well deserved, and we're looking forward to your talk.
Okay, thank you, Klaus, for the most kind introduction. And I wish to start, of course, by saying that I'm deeply honored. I'm delighted by receiving this prestigious prize, and I thank to all those who contributed to awarding it to me. I shall do one thing. I like to have, something like a chalk to draw with. There were excellent talks already on this subject, particularly by Klaus Bartschat, also at the occasion of his receiving the Allis Prize. And this was at the GEC 2017 in Pittsburgh. And then I had a talk on the same subject 10 years ago at the GEC in Paris. There are excellent reviews on this subject by Klaus Bartschat and Mark Kushner, 2016. That's it. By Klaus Bartschat, 2018. And then more plasma-oriented by Zoran Petrovic, 2007. About GEC, I belong to the lucky generation who still met the grand pioneers, the founders and early speakers of the GEC conference series. I met Frank Biondi. Art Phelps told me a lot about the GEC, in particular that there was a lecture by Will Allis on the history of GEC, 1972 at the 25th Gaseous Conference. He actually gave me a transcript of this lecture, which was very interesting, but I'm ashamed to say I lost it. At the chaos of my liquidating the office before my retirement, it got lost. So if you have a copy, please let me know. All I have is small fragments which I scanned a long time ago from which you can learn that Art Phelps was chairing the conference, the MINS conference, 1956, at Westinghouse in Pittsburgh for the second time. There were 48 papers, 70 participants. A personal remark, my first scientific conference ever was a GEC. I was a postdoc at Yale University, and we went to attend the 32nd GEC, also in Pittsburgh, at Westinghouse, 1979, chaired by Peter Gentry. There are already more participants. GEC has grown. Now, a person who affected me, influenced me very strongly was George Schultz, also one of the founders, one of the very early speakers. And that's why I want to dedicate a slide to George Schultz. I wanted to join the group of George Schultz as a postdoc, but most sadly, George Schultz died very prematurely at the age of 50. But I joined the group anyway, which was led at the time by Shek-Fu Wong, and I enjoyed it. I learned a lot. The spirit of George Schultz was still around. George Schultz was born in Czechoslovakia. I was born in Czechoslovakia, so that's one more link between me and George Schultz. As you all know, the most spectacular discovery of George Schultz was this resonance in helium atom. And I loved this curve. It fascinated me so much that I spent essentially all my research time with the uncountable facets and varieties of resonances in atoms and molecules. Now, what do I want to reach in this talk? My specialty is measurement of high quality cross-beam data. And when I built up the infrastructure, learned how to measure high quality data, I had a naive idea that I shall go to people doing plasma modeling, and they will be waiting eagerly for my cross sections, will use them for the plasma models, and it will lead to revolutionary applications. And I had to learn that this will not work that way at all. I learned this at couloir discussions, coffee breaks at conferences, very often from Zoran Petrovic. They told me, see, your cross sections are useless for us because they do not form a complete set. We need a complete set. All final state, all processes, all energies from millivolts to kilovolts, all scattering angles, or at least integrated over all scattering angles to get integral cross sections or momentum transfer. Often we need cross sections for things which are impossible or very, very difficult to measure. The target may be unvolatile. Like if you ask me to measure iron atoms, I couldn't do that because iron atoms do not evaporate to go into the machine. As a matter of fact, if I remember correctly, Klaus Bartschat asked me to measure iron atoms, right? I never did for obvious reasons. The target may be very poisonous. You do not want graduate students to be exposed to it. The target may be reactive intermediate in the chemical scale sense. It will polymerize and not go into the machine. Cross-sections are needed for targets in electronically or vibration excited states. All this cannot be measured. So what we need to save us is theory. But if I dare to say so, theory is not entirely without problems either. Theory rarely comes with error bars, with confidence limits. So to gain confidence into the predictions of theory, one has to check it with selected cross-beam data, which can be measured. As complete as possible, as much data as possible. And once you are convinced that theory reproduces the cross-sections correctly, you use theoretical cross-sections as an input to plasma modeling. So the crucial connection in this diagram is actually from here to here. And this is what I shall be talking about. Right? Compares validating theoretical cross-sections by comparing to experimental cross-sections. So finally, this is the roadmap, the table of contents. I shall spend a few remarks on the technical aspects. First, the technical capacity of the instrument is crucial, very important. And second is that I liked these things, engineering part of the thing, just as much as the science. Major part of the talk will be this comparison, excuse me here. Theory, experiment, electronic excitation of rare gas atoms, of polyatomic molecules, vibrational excitation of polyatomic molecules, and one quick remark about dissociative attachment. I shall not talk about how these cross-sections are used in plasma models because it's not my specialty, and time would not permit anyway. And if time remains, I shall bring something what is close to my heart, what really amused me the very few last years before my retirement, last years, last months, even last weeks. And who knows, maybe there will be a connection to plasmas. Anyway, this will be my question to you. And this thing is, in a modest sense, new kind of spectroscopy, two-dimensional electron energy loss spectrum. So finally, the first chapter, technical remarks. And I shall start with a personal note. I have a lifelong fascination with free electrons, well, nearly lifelong. I started at high school. When my parents gave me an old radio set, I took it apart and constructed all kinds of other devices from it, like this one. And the old-timers among you will recognize this device. It's an electron valve, electron tube. A pentode. It has a cathode to make free electrons, grids, electrodes to steer the electrons, and anode to collect them. So this was my first electron impact spectrometer. Right? Then when I was a PhD student in Basel, I built another sort of electron spectrometer thanks to John Mayer, my PhD advisor, to whom I owe so much. And then I went to Yale as a postdoc, and I enjoyed it a lot. It fascinated me. But one thing bothered me, and this was the instrumental limitations. I would come and say, why don't we measure the cross-section for this high vibrational level to learn something about the high end of the resonant potential? And I was told, no, Michael, you cannot do that because the cross-section is small and the machine has high background of stray electrons. The signal will drown in the background. I would come and say, why don't we measure this threshold peak? Isn't that curious? And I was told, no, Michael, you cannot do that because the machine does not work below 1.5 electron volt. I said, why don't we look at the extreme angles like 180 degrees? And I was told, no, you cannot do that because the analyzer and the source of beam cannot be at the same position. So I started to dream about building my own machine, which would bypass these limitations. The machine of my dreams, the dream machine. And then something unexpected happened. I got a position at the small chemistry department in a small city in Switzerland, Fribourg, and I was given the money, and even more important, I was given the time to build my dream machine, and it's here. I have to admit that there is nothing revolutionary about it. It's the same hemispherical analyzer machine, but I paid attention to all kinds of details, where to put slots, slits, what size, what lenses, and so on. The only thing which is revolutionary is the magnetic angle changer, which extended the angular range to really 0 to 180 degrees. Oh, this is a photograph of the hemispheres, everything, excuse me, everything made of molybdenum, titanium, all kinds of electrodes and deflectors. The magnetic angle changer, the revolutionary part, is not my invention. It's Reed and Channing. I remember, like if it were yesterday, once I arrived at a conference in Great Britain, and Frank Reed comes to me beaming and says, Michael, you will like this. And he was right, I liked it. The only thing was, I told myself, why did not I think of it myself, right? Because if you know how it works, it's very self-evident. what you have here is what other people called actively shielded solenoid, a device which is commonly used in magnetic resonance spectrometers, magnetic resonance tomographs. The only thing which I did bring is how is it realized? My magnetic angle changer is not a bulky solenoid, but something very filigrane, very thin, nearly transparent. So it does not interfere with the gas flow from the nozzle. Well, the magnetic angle changer is there and does not make the performance of the machine any worse than it was before. What is also important is that the temperature is constant of my device because it's cooled by water. It's wound from thin copper tube and there's high pressure water going through it, even when the current going through the whole solenoid changes. And this is very important because the machine drifts when the temperature changes, so it would never work without the cooling. Okay, so my dream machine was ready. Was it any better than existing machine? And this question was addressed by my many years friend, colleague, mentor, Hartmut Hotter, who wrote a most kind editorial on the occasion of my retirement. And he put in these cross sections of N2O. The solid lines are Fribourg data from the dream machine and the symbols existing data at the time. At the top, elastic cross section, and here, here, vibration in elastic cross section. The good news is for elastic cross section, the existing data and the Fribourg data agree, both in magnitude and in shape. The vibrationally inelastic data existing agree with the Fribourg data in magnitude. Whom are they from? Of course, Hiroshi Tanaka. They are the big names in measurements of cross sections. So Bratislav Marinkovic, Johnston and Neville, Hiroshi Tanaka, Steve Putman. But I dare say that the dream machine did bring something. It extended the energy range of the elastic cross section. So here is 50 millivolts, like on a good days, maybe even 40 millielectron volts. It extended the range of sensitivity. I could measure this cross section, which is orders of magnitude below the elastic. And instead of single points here, it gives me the shape of the curve. So it tells me something about the physics, two resonances, and then a very deep dip, and then very high threshold peak. There is even fine structure. The zigzag here is not noise, it's real structures. I have only a fuzzy idea what are they due to. So if you want to please me, please calculate that as long as I am around, so that my curiosity is satisfied. So the answer is, with all modesty, I claim that the dream machine greatly expanded the area into which one could look. Right? So the horizons widened. It's like when a biologist gets a better microscope and an astronomer a better telescope. New horizons open, you can go and look at things which were inaccessible before, and that's what I did. This is a side remarks. The machine does not really measure absolute cross sections, only relative. So we have to normalize to helium, which means that one needs reliable helium data. And actually it's needed also that everyone uses the same data, right? I always use the data of Nesbett. It has two little catches. It's a bit old and it stops at around 19 electron volts because it does not include the excited states, electronically excited states. So it was very helpful that Dmitry Fursa and Igor Bray later provided very high quality helium cross sections as a check and extending to higher energies. But the result is that the Nesbett data was very good. Actually, you can barely see the difference between Nesbett and Bray and Fursa. And then, yeah, that's it. This is using intermezzo. So what I talk about is, will electron spectrometers help plasmas? One can also ask, do plasmas help electron spectrometers? The trouble with electron spectrometers is that they become dirty as they operate. You see, there's a layer of a polymer forming here, which causes, it's not conductive, it causes surface charge, unwanted electric field. One has to open the machine and clean it every so many weeks. And it was actually at the GEC that I heard about, how do you call it, atmospheric pressure dielectric barrier discharges. And I thought, well, maybe this will be nice for cleaning. So this is the plasma pen pointed at this electrode. And after about 2 minutes, it looks like that. Shiny, clean. Right? There's only one problem. The machine did not work. And I don't know why. Maybe there is a transparent layer of something insulating made by the plasma pen, which causes it not to work. So very probably this could be improved somehow, but life is short. There were other things more important. Conclusion on technical remarks. The limitations have been overcome in many instances, in particular angular range, low energy capacity, a routine correction for instrumental response function, low background of stray electrons below half a count per second. And the best news is that the instrument was not scrapped after my retirement. It moved to Prague, where it's now operated in the most qualified way by Juraj Fedor and Jaro Kočiček, which is not self-evident at all. So this is my great satisfaction. Chapter 2a, the great names in theory are Klaus Bartschat and Oleg Zatsarini. They developed a method which I shall not describe to you because it's not my specialty, but it's the B-spline R-matrix method, the basic version, and then finally the fully relativistic scheme, which is Dirac B-spline R-matrix method. How does it compare to the experiment? So this is to remind you of the excited states of neon revealed by electron energy loss spectroscopy. It also shows the instrumental resolution. So these states can be nicely separated by the instrument. The resolution is sufficient. This state as well. But there are many states which overlap, which I cannot measure. The cross sections, the first test is elastic. It's easiest to measure. The circles are Fribourg experiment. The solid line is the B-spline theory, and they agree beautifully. Now notice that the experiment really goes from 180 degrees all the way, okay, not to 0 degrees, because the machine cannot distinguish between unscattered electrons and forward elastically scattered electrons. So, but it ends at about 8 degrees, which is quite good. Now, what we really want is electronic excitation. Examples, 4 states. Left is Fribourg experiment. Right is the Zatsarini-Bartschat theory. I emphasize that both data have their own absolute scale. They are not normalized to each other in any way. And they agree marvelously, beautifully. It's like the puzzle in the Sunday paper, right? Find the 10 differences. So let's go look for the 10 differences. You will not find 10 differences. So this was incredible. I was greatly impressed. These are 2 higher lying states, also very nice agreement. This is an expanded view, horizontally expanded view, so that you see also the width and the shape of the peaks, and even that agrees. This peak is very narrow, this one is wider, and it's asymmetric. Everything is reproduced by the theory. Absolutely amazing. Again, no normalization of one data set to the others. Both are absolute. Angular distribution for 5 prototype shapes, states. Red circles data from Fribourg experiment, blue line, continuous line, B-spline theory. And the agreement is also beautiful, great. Notice that the experimental data here goes from 180 degrees all the way to 0 degrees here, because the machine can distinguish between unscattered electrons and forward elastically scattered electrons, because they have different energy. So it can be done, but to do it is not all that trivial, because imagine the unscattered beam goes directly into the analyzer lens and is many orders of magnitude stronger than the scattered beam I'm looking for. So one needs a very good attenuation of stray electrons to get this data. Krypton, relativistic correction is already necessary and is also very nice. And the ultimate case, xenon, very heavy relativistic correction. Different orbitals are necessary for different state, which needs non-orthogonal orbitals and so on. And the agreement is less perfect than in neon, but it is still very impressive. The important thing is that the absolute value is okay. Again, no normalization of experiment and theory. But there are small differences, like these resonances are not in the calculation. The calculation says that the cross-section goes up here, and the experiment that it stays flat. And this resonance is more pronounced in experiment than in theory. Okay, this is more states, like very nice agreement. This is electron energy loss spectrum, reminding you that xenon has many, many states which I cannot resolve. So after this, Oleg and Klaus went and made another calculation, this one, the Dirac B-spline calculation with many states. That's the red curve. And it improved essentially everything. Like all these resonances are now here. The cross-section follows about the experiment rather than going up. And then if you look another picture, what was in the early calculation only a shoulder is now there's a peak in agreement with the experiment. So this is great, even xenon. And xenon has application. This is simulation modeling of plasma, xenon plasma in satellite engines. And what these people did is they measured the infrared emission and compared it to theory to understand what's going on in this plasma. And of course, Oleg and Klaus provided all the cross-sections. This diagram is here only to show you that there are many, many, many states which you need to calculate, you cannot measure. Also, the theory provided the oscillator strength needed to reproduce the emission spectrum. The nice thing is that the first author is Rainer Dressler, who was my first PhD student in Fribourg many, many years ago. So this is using the original model, and then there is a follow-up, 2019 follow-up, using the full correction of relativistic effects. Conclusions of noble gases, amazing success of theory, and excellent illustration of the strategy. Use experiment to verify the reliability of theory, and then use theory to provide cross-sections for the modeling. Again, electronic excitation of polyatomic molecules. The great name in theory is Ximena Gorfinkel and her younger co-worker, Alessandra Lopas and Zdeněk Mašín. Ximena had a lecture yesterday, so there may be small overlap between these two lectures, but the data is so nice. You can see it twice. They use R-matrix method, but in a very advanced, very inventive way. So it goes, these calculations are amazing, go far beyond what was around before. It includes also a delay time analysis, which tells us about resonances, and this is what I love. Example, pyrimidine. It's told to be model for nuclear bases. This dissociation of nuclear bases are important for radiotherapy of cancer, and electronic excitation is the initial step for dissociation. So electronic excitation is important. How does experiment, the red line with statistical noise, compare with theory, the blue line on the top? As cross-sections go, this is an amazing agreement in terms of magnitude of the cross-section. Again, no mutual normalization to each other. Experiment and theory are on independent vertical scales. Beyond that, there is a very nice agreement in the resonance structure, which pleased me very much. Right? This calculated resonance gives rise to this shoulder. Okay, the experimental resonance is wider than calculated, but this is understandable because the calculation is at fixed nuclei, whereas the experiment includes vibrational excitation, the Frank-Condon profile, which makes it wider. Then this resonance, excuse me, this resonance is calculated here. So it's a little bit higher, but that's excusable because we know the reason. It's because not fully taken into account the polarizability of the target. This experimental resonance is here in the experiment. This experimental resonance is here in the theory, also nice. And then this experimental resonance is also here in the theory. And what the theory provides, what the experiment doesn't, is the justification order, the explanation. So I was delighted to see that and read about what's the orbital occupation of this and that and how does that happen. This was very, very nice. Another target, thiophane, again, this statistical noise experiment, solid line theory, it agrees very nicely. Here you understand now the Frank-Condon profile makes it wider. So also a very nice agreement. Now, very recently, 2020, there is a calculation of thiophane by Romalie da Costa and the people around her. They used a completely different method, Schwinger multi-channel method with pseudopotentials and status exchange plus polarization potential. And here, the line with statistical noise is experiment, the green line is their calculation. So it's also very encouraging. The calculation ends at 7 eV though. The Armatives calculation goes to 16 eV, which is an advantage. Conclusions, amazing success of theory, magnitude of the cross-section correct, resonance structure is correct except for the shift due to polarization. Inspection of time delay identifies the resonances, provides assignments of the resonances, especially such question like what is the parent state of what state, and then configuration mixing in the resonances, which I find fascinating, right? We divide resonances into core excited and shape. And Kimena shows us that this is not quite true, that they mix. You have a certain shape aspect and certain core excited aspect. And the theory tells us everything about that. So my challenge to the theory is, could you calculate conical intersection between these resonances? Vibration excitation of polyatomics. The names in the theory are Roman Churik, Petucharsky. They call their method discrete momentum representation method. Of course, vibration excitation in diatomics has been studied a lot, but in polyatomics, this is a pioneering work. Polyatomics have many modes, and they calculate the cross-section for all modes. So they can reproduce the energy loss spectra also on absolute scale. There is no normalization of experiment, the black line, and theory, the red line. I cannot resolve the individual vibrations, right? This is the elastic peak, that's my resolution, and these vertical bars are the vibrational peaks, they are too close. So what they did is convolute the calculated spectrum with a profile based on the elastic pipe. And the profiles agree very nicely. So it's a success of theory. This is incident energy 5.5 eV, here 10 eV, also very nice agreement. As cross-sections go, this is not a significant deviation. And as in the case of electronic excitation, the nice thing about theory is that it provides insight into what's going on. So there is a resonance with this orbital occupied. It's an F-wave resonance. It's anti-bonding with respect to CC bond length. So when an electron comes here, the ring stretches a little bit. When the electron goes away, it leaves the ring in vibrating state. So you get ring vibration excited, totally symmetric. And the theory tells us that the incoming electron comes in A2 prime symmetry and leaves, of course, also in A2 prime symmetry, because the vibration is totally symmetric. So the symmetry of the vibrational wave function is the same before and after excitation. Less evident is this resonance, which excites non-totally symmetric vibration. So how does that happen? The theory tells us how the electron comes in the A2 prime partial wave and leaves in a different partial wave, A2 double prime. So the change in the symmetry of the vibrational wave function is compensated by the change of symmetry of the partial waves. So beautiful insight gained by theory. Conclusions: all vibrational modes treated, we calculated or they calculated benzene many modes and provides understanding of the mechanism. Dissociative electron attachment. The name is Ilya Fabrikant, and then also Wolfgang Dunke, Martin Žižek, Ivo Racek. Only one example, HBr and DBr, experiment red, calculation dashed blue, and there is non-local effect calculation respecting non-local effects. And it agrees beautifully with the experiment in terms of shape and in terms of size. In particular, the calculation reproduces the interchannel coupling. See? Where new channel opens, vibrational excitation at V equals 3 threshold, the dissociative attachment cross-section drops because the extra flux goes into vibration excitation. This is reproduced by theory, and you need non-local theory for that. So this slide emphasizes that in some cases, not all cases, you need non-local theory. Use in plasmas. You most probably saw this beautiful slide by Mark Kushner showing that there are many everyday plasma applications which normal citizens do not even dream about. There is one more connected with COVID. I saw this in Chemical and Engineering News 2 weeks ago, so I put the picture here. How to make vials for vaccination, not out of borosilicate glass, as most people do, but out of polymer, olefin polymer, and then coat them inside using plasma-enhanced chemical vapor deposition to make them compatible with vaccine. Another example from Prague. Juraj Fedor, Jara Kočiček, I already mentioned their names. They measured cross-section for this gas, which is a promising alternative to SF6 in high voltage switches, but much more compatible with climate. They measured these cross-sections, and these cross-sections went into plasma model and are actually useful for something applied. Complete set of cross-sections in HBr collected by Zoran Petrovic and the people around him. You see, like I could never measure this. The energy is too low even for me. We are not equipped to measure neutral dissociation. But you will recognize the dissociative attachment spectrum. the red line with the step downs. Yeah. So we did contribute something. N2O, again, complete set of cross-sections from Zoran Petrovic and people around him. You will recognize these three curves, the 3, 4, and 5. You already saw them. This is vibrational excitation of N2O with the two peaks and the dip and threshold peak. Something from a different group, Gustavo Garcia. They published this year an impressive set, complete set of cross-sections for pyridine. Time, oh, I shall not have time to talk. No, I do. It's 41 minutes. You choose me, it's fine. Two-dimensional spectra. So I'm changing the subject a little bit, but who knows, maybe you will find applications even in plasmas. Actually, the idea to plot electron energy spectra as a two-dimensional plot is quite evident because the collision is given by incident electron energy or residual electron energy. So my first two-dimensional spectra is from 1985, the early days of computers. So what I had to do in those days, it take scissors and cut out the individual cross-sections and glue them on a piece of paper. So this is very early two-dimensional spectra. Now the modern version. I have to quickly introduce something what you already know, namely how does electron energy loss spectrum work? Right? You hit a molecule with electron energy EI, incident electron energy, which decides in what state, what intermediate state you make the target in. And the electron goes away with a smaller, possibly energy, residual energy ER, and the final state of the target is given by the difference of these two, the energy loss. For electron energy loss spectrum, you take certain incident energy and then sweep the residual energy and plot it against electron energy loss. Electron energy loss 0 is the elastic peak, that's here. Then you have inelastic peak, the various final state, vibrational final state here. And at one point, you measure 0 eV electrons, that's the thresholds for excitation, and that's the end of the spectrum. Now, let's take several spectra. With increasing incident energy, small till higher. The spectra get longer, of course. The threshold is further and further away. So all the thresholds, all the elastic peaks, like on this line, elastic ridge, and all the threshold happen on the dashed line, that's the threshold line, and everything interesting happens in between these two lines. An example, benzene. Here to remind you, so the incident electron energy defines the initial state. In particular, when you hit the resonance energy, you make the resonance state. And the energy loss tell you what are the final state, vibrational states of benzene, small frequency, higher frequency, overtones, and so on. So don't forget, attachment defines the intermediate state, energy loss defines the final state, and you can also see what is the energy of the electron which just left. It's the distance from where you are and the threshold line. Now, how do I interpret this? Of course, one could calculate it, but I think it's beyond the capacity of theory right now. So I have a very naive qualitative interpretation. I say that this experiment is actually a hidden pump and probe experiment. The pump is attaching the electron, making the nuclear wave packet in this state here. Then the nuclear wave packet relaxes, so time runs. It relaxes for a given amount of time, and then it rains down, falls down, and you can tell where did it go, what is the final state, because you know the frequency of the vibrational state where it ended. So you have to pump, you have to probe, and then the weakness is, of course, that the delay time is not precisely defined, but it's in a way defined, because if you wait longer, then the energy of the emitted electron is smaller. So as I move along the spectrum in this direction, I increase the delay time. So this is poor man's pump and probe experiment. So again, I attach the electron, then it relaxes, and I can follow it as it relaxes, and it becomes smaller and smaller, the nuclear wave packet. So the amount of electrons emitted becomes smaller and smaller, right? There's a little signal here, and then there are virtually no electrons near the threshold time. So, well, fine. I saw that every molecule will work like this. This compares benzene, which we just saw, and pyridazine, which is chemically very related. It's isoelectronic. It's only 2 CH groups are replaced by slightly more electronegative nitrogen atoms. So I would think that this will be the same thing as benzene. Maybe the resonance will be a little lower in energy because of the electronegativity. And I'm completely wrong, right? It's dramatically different. It's completely something different. Right? Here the electron is attached. The nuclear wave packet moves down, becomes weaker and weaker, and falls down into discrete vibrational levels. So I call this the island of discrete excitations. I know from transmission spectroscopy that the resonance in pyridazine is here. So let's attach the electron to form the resonance. That's here. And then let's wait for the discrete excitation as the system relaxes and falls down into vibrational levels. There's nothing here. Where did the electrons go? Aha, they are here. What does that mean? This is the threshold time. So these are very, very slow thermalized electrons. So the small chemical change completely changed the behavior. Pyridazine is a super sponge for electrons. It soaks up the electrons and then gives them off dropwise very, very slowly. Now, okay, what do I want? I shall return one slide, excuse me, because I want to show you this potential diagram. What does that mean? It means that in pyridazine, we attach the electron, we have the nuclear wave packet here, and then we never see it here. It has never been in this range. And it suddenly turns up here, where the energy of the emitted electron is very slow. What happened? My qualitative explanation or proposition is that it's a fault of a conical intersection. What happens, this nuclear wave packet, instead of traveling on this potential surface, it finds a conical intersections nearby and bloops, goes like through a funnel into the low-lying state where all the vibrational modes are excited to some degree, just a hot negative ion. So I believe that's what happens. That's why I said I would like to see conical intersections from theory. Chlorobenzene is like benzene, except that dissociative attachment channel has opened. The chlorine can come out as Cl-. And it looks like benzene, actually. You have island of specific excitation, discrete excitation, then the signal becomes weaker and weaker, and whatever survives through the stabilization point comes out as Cl-, and I measure that as well. This is the Cl- coming out. So chlorobenzene is like benzene, except dissociative attachment. Now let's modify it chemically by replacing one CH with the isoelectronic nitrogen. And the same dramatic difference in the spectrum. Here, okay, I know the resonance is someplace here. You attach it, and you do not see the nuclear wave packet moving here. There is no island of discrete excitation. All the electrons come out with nearly zero EV energy. What does that mean? The dissociative attachment works completely differently. Here, the nuclear wave packet slides on a potential surface and comes out as Cl-. Here, The nuclear wave packet does not slide along the potential surface. There is no signal here. So it must fall down through conical intersection. And then you have hot negative ion, which dissociates thermally. So the dissociative attachment spectra of this molecule and this molecule look similar, but that betrays the mechanism is absolutely different. Conclusions for 2D spectra, they reveal the dynamics of the negative ions, not only their energies. Small change in structure dramatically raises the power to stop power of the molecule to stop electrons. So I thought, well, is this not interesting for plasma? If you have electrons sponge suddenly in the plasma. And my wish for theory, please calculate the conical intersection. This is a remark for Jimena Gorkin. Of course, there are many colleagues who do magnificent work in electron collisions, both theory and experiment. I could never mention them. So this is my excuse slide. I could not mention. Yes. This is the end. I claim that this is aesthetically quite nice. No? I think this is a piece of art created by nature. Thank you. I'm a little bit ahead of time.
Okay.
Thank you for your attention.
Okay, thank you very much, Michael. That was just a beautiful talk, and I hope people can hear me, but I can see my microphone should be okay. So I have indeed a couple of questions and some very assuring comments. Tom Miller will send you information about the GEC history stuff, including Will Allis's notes about the talk. And Greg Zever also knows something about it. So hold on to these two guys. Then the question that made it high up is, Michael, there is sometimes confusion about elastic cross sections. Sometimes they include rotational transitions and sometimes not. Could you specify what is meant by elastic in the sets you have presented?
It's all integrated over all rotational transitions. Because I do not have enough resolution to resolve the rotational transitions. And in certain molecule like HBr, where the rotational quantum is quite large, I see the elastic peak to broaden but I do not take the height of the peak. I integrate under the peak. So I integrate all rotational transitions into it. All my so-called elastic cross sections are rotationally inelastic. Is that okay?
Okay, great. Another question that I have here is, it says, the measurements of vibrational cross-sections for polyatomic molecules have very small energy loss. I expect that requires extensive time for counting to get acceptable statistics. What is the typical elapsed time for such measurements?
Let me find. Do you mean this?
I don't know what the question means.
I think these spectra have small energy losses, so I presume this is what is meant, right? Energy loss is 100 milli-electron volts. No, I'm not sure. For vibrational excitation, the signal is usually quite strong. Problem is with electronic excitation where the signal is weak. So
well,
there is not much of a problem.
I can't see a follow-up, but maybe you can tell us. I mean, it might be a good idea.
Anyway, the question is good. How long? I like spectra which are nice, right? Low signal to noise. So even when it's not necessary, I count it for a long time. So the way to operate the machine is let it count all the time, over weekend, day and night. So the acquisition is usually many hours, just to make it nice.
And you don't have any, I mean, you know, being a theorist, you can in fact keep all the conditions stable. You know, you mentioned something about cooling and, you know, that things like that. I mean, that must be, I can imagine that something will drift.
Yeah, of course. Yeah. You have insight, yeah. it can be kept stable. I mean, when you introduce a new sample, the machine drifts. And then it stabilizes, and then you can keep it stable of maybe 8 hours or so. But then you need to come, retune the machine, and restart the accumulation. So I was tight on the weekend every time. Christina Regeta and all the graduate students, we changed, like, you will come at that time, I will come at that time, to retune the machine to avoid the problem which you just mentioned. It's a very real problem.
Very good.
Okay.
I don't see any other ones. It's funny if they get reordered here. So if somebody has something to say or to ask, this is your chance. I'll give it another 10 seconds. If nothing flips up here, then that's it. Let me just say the comment is, yes, we are still waiting and hoping, and we are working, in fact, with Jurai Feder to try and fix this xenon problem. Xenon is tough.
Yeah.
But
we
are working on it. We are working on it.
Yeah, same thing experiment, one can do it. Yeah. Actually, before retirement, I bought xenon.
That's right.
But life is too short, right?
You told me that
I never got
going
around
to spend the last 5,000 euros on a bottle of xenon.
And then it got wasted because you are not allowed legally to bring it to Czech Republic, right?
Really?
You are not allowed to cross the border with the bottle, so we had to return the bottle to them.
There you go.
Yeah, there. But Jura is around, and
yes,
he's really mastering. He's mastering
so.
The machine. He does. He makes very nice spectra with his coworkers.
Very good. So I think there's nothing came anymore. So thank you again for this beautiful talk, beautiful overview. I'm sure you could impress a lot of people, certainly me. So with this, thanks again.
Was my pleasure. It was my pleasure.
I'm closing the session then. Thanks.
Bye-bye.